process began by outlining aims for the project, these being designing and optimizing a wing spar to support a wingtip load both in shear and in torsion. The goal was to engineer the spar to withstand as much force as possible while having the lowest mass. Some basic requirements were outlined in the briefing. The wing semi-span must be 0.74 meters, plus a 0.1 meter root to attach the wing to a vise. The wing must be made from 5mm laminated foam board. The aircraft will weigh 2 kilograms, and max load factor will be 2.5. The maximum compliance will be less than 15 millimeters deflection at 1 g, and less than 3 degrees per Newton meter for the torsional compliance. The process is structured into 4 phases: conceptual, preliminary, detailed designs, and then acceptance, allowing for an iterative design including testing and prototyping. Research began, closely linked with the data output from the Excel sheet. Concepts were drawn up on paper to fit with some hand-drawn free body diagrams, bending moment diagrams, and shear force diagrams. A few possible solutions such as circular beams, I-beams, and box beams were presented. To find a good balance, the second moment area and second polar moment of each structure would have to be calculated and applied. The data showed that I-beams preformed the best in direct stress or shear stress, whereas its torsional compliance was poor. Circular beams had the opposite results and performed well in torsion, but performed poorly under bending. Box beams were a good mid-ground for both. Using this new knowledge, the Excel model was put through rigorous testing until an ideal dimension was chosen. This was to be 48 millimeters by 56.5 millimeters, with a crossbar running along the center for more bending and torsional strength. A safety factor was then implemented to ensure that the load imposed on the beam doesn't cause it to break prematurely in case of manufacturing faults. To test a few different dimensions for the wing spar, another 2 Excel models were written in the sheet to determine passing and failing parameters. This accounted for direct stress, torsion, and moments about the bracket. A prototype was conceptualized and built in the lab, but proved to be quite heavy. The beam was more than capable of supporting the loads, but was not the optimal solution. The first design did not leave enough room for the top and bottom of the aerofoil ribs, leading to design 2, where the shear stress gradient along the spar was considered. This gave us a staircase design which had 15mm thick top and bottom walls at the root, and then decreased in 5mm increments along the spar. This optimizes the stress distribution and still saves weight. The next stage of the process was to model and simulate these spars and wing ribs in a CAD software. SolidWorks was used in this project as it allows for simulations to show how deflection and torsional stresses affect the beam. CAD was also used to design the wing ribs in accordance with the requirements outlined in the conceptual design. These are often quite heavy elements in a wing, and so focused on removing weight by cutting holes in the ribs while still preserving their structural integrity. To combat this, the scoring tool was used by the laser cutter, and the hole for the spar was cut by hand. Once this was done, all parts could be sent to the laser cutter and can be cut ready for final testing. The spar was built and tested to see if it would pass the outlined tests. This proved to be close to the optimal solution and needs minor adjustments ready for the final showcase. Should more time be allocated towards the project, a lighter and more structurally stable spar could have been made and optimized further. Overall result for this project showed the group had good communication and persistence to generate an optimal result.